Hey all, I hope all is well going. Whoa, I hope all is going well. I decided to go thermonuclear on you today. Nuclear, because it's going to get crazy. We're doing confidence intervals, which you're about to find out are awesome. So let's look at the notes. So I want to start it off by just looking at a little recap of what we learned pretty much last time, but kind of in the last few days. So one thing is that we talked a lot about the sampling distributions of sample means and sample proportions. So I've labeled this axis as sample means or sample proportions because both of those have a bell-shaped distribution called a normal distribution. Unless we're in a special case where we don't know the standard deviation of the sample mean, then we actually use what's called a t distribution, which we'll talk a little bit more. But the logic is all the same. You really don't have to worry much about that. All that happens to this guy is it gets a little bit wider if we're dealing with that situation. And that's why we talked briefly about t distributions in the last video. But you probably saw this in your last class. So if we have a normal distribution, then 68% of observations will be within one standard error. So if we took a bunch of different random samples, took a bunch of different random sample means, because remember, sample means are a random variable, about 68% of those would be within one standard error of the true mean, mu. Similarly for sample proportions. If we took tons of different surveys and asked how many people approved of Donald Trump's job performance or something, there's some true proportion out there. 68% of our calculated sample proportions would be within one standard error of the true population proportion. Oops. Okay, and then we can also get numbers like that for two standard errors. 95% of observations will be within two standard errors. So between -2 and +2 standard errors. And almost 100%, 99.7% will be between -3 and 3. These numbers are a little bit rounded, as we'll actually see in a second, but that's like a general rule you can use. So sample means will fall within certain distances, for example, 1, 2, 3 standard errors, of the population mean with different probabilities. So this is just an example of that, right? With increasing probability, we get farther away. So if we widen the target, there's a higher probability we land in there. Like for this example, we have a really wide range, 3 standard errors, so we get almost all of our observations within that range. Now we can use z or t distributions to get any probabilities we want instead of just memorizing these 3 cases. So in the last video we did that, right? We picked kind of different ranges and we're able to calculate the probabilities of landing in those ranges by using z statistics. And we could do the same thing with t statistics. So today's video is about using this idea that we don't just have to stick to these ranges right here to calculate confidence intervals. So what this graph, just what this says is that 68% of sample means will land within the population mean. And last time when we were doing the problems, we pretended we knew the population mean. But usually the point of statistics, part of it is to try to guess the population mean or estimate it. That means we don't know the population mean. So in most cases, we will not actually know the population mean, and we'll be trying to use the sample mean, x bar, to guess what the population mean is. So let's flip the logic this logic on its head real quick. If there is a 95% probability that a random sample mean is within 2 standard errors of the population mean, then it also must be true that there is a 95% probability or chance that the population mean is within 2 standard errors of the sample mean. It's kind of like saying, hey, if there's a 95% chance that I'm within 10 feet of you, what's the chance that you're within 10 feet of me? It's still 95%, right? We're just changing kind of the center of the question. So if there's a 95% chance that a sample mean is within 2 standard errors of a population mean, then the opposite must be true too. There must be a 95% chance that the population mean is within 2 standard errors of the sample mean. So make sure to think about that, because that's some important logic that'll kind of we'll have to keep with us for the rest of this class. So make sure to kind of understand what that paragraph is saying and think about it if you need to longer. And that's one of those things, I call it the statistics chair. It's good to put a chair in a dark, damp room somewhere in your living quarters and just sit in it and think about statistics sometimes. Because oftentimes we're just trying to crank through the math and we're never stopping to think about the logic of what's going on. And stopping and thinking about the logic of what's going on is very important in statistics. And this is one of the first big examples of that. So just stop and think about, yeah, that must be true. Even though we don't know the population mean, because we know that 95% of the time a sample mean is within 2 standard errors of the population mean, it's also true that 95% of the time the population mean will be within 2 standard errors of our randomly generated sample mean that we generate from a random sample, remember. So now let's get down to actually figuring out how to calculate these things. So it turns out that this up here, this 95% within 2, is actually rounded. The true value in a z distribution, which you can think of these numbers as numbers of standard errors. Because when we calculate z right here, we normalize by the standard error. And by dividing by that standard error, we're converting whatever our underlying variable is, whether it be dollars or inches or feet or pounds or grams. We're converting that into the language of statistics, which is standard errors when we calculate a z. And by doing that, when we label the axis z for a standard normal distribution, you should think of numbers on the x-axis right here as standard errors. So what this says, remember we have 0 at the middle of this guy. What this says is that, wow, that's crazy that just changed my 0 into a perfect circle. I love it. This says that if we go 1.96 above 0 and 1.96 below 0, then 95% of our observations will be in that range. So that says it's actually not exactly 2, it's 1.96. And so that's just a reminder of what that z is right there. And so notice there's actually, I've written an Excel formula right here, which I'll show you in the next part of this video. Last time in the Excel video, we used norm.dist, a normal distribution. We put in a z value and it spit out a probability. Well, there's another cool function that does the opposite thing. We put in a probability, for example, 0.025. 0, remember, is the expected value in a standard normal distribution. 1 is the standard error in a standard normal distribution. That's why you can think of it as number of standard errors, because it's just 1. It's a 1-for-1 relationship. And that gives us actually minus 1.96. Why did I put in 0.025, by the way, for 95%? Well, if we think about it, remember that these distributions are always thinking about the area to the left. So if I'm taking 95% in the middle, I have two dividing lines right here. There's a 95% between those two lines. Well, if there's a 95% between those two lines, then outside that line on the left, there must be 2.5%. And outside it over here on the right must also be 2.5%, right? Because that means that 2.5% plus a 95% in the middle plus this other 2.5% adds up to 100%, and it always has to add up to 100%. So by putting in 0.025, the probability version of 2.5%, this function will actually spit out the number minus 1.96 to tell me, hey, this is the number of standard errors you have to go to the left of 0, so that there's only 2.5% to the left of that number. Now notice by the same logic, because this is symmetric, how much is to the left of this line right here? Well, if there's 2.5% to the right, there must be 97.5% to the left, because those two add to 100%. So z 0.025 is how I write this. That's going to be minus 1.96. The z value that has 0.025 probability to its left, that's minus 1.96. Z 0.975, the z value that has 97.5% to its left, is positive 1.96. That shows again that this is a symmetric chart, because we get the same distance either way from 0. We just get the positive of the same number if we go to the right. Okay? So what this says, if I take my sample mean right here and subtract 1.96 standard errors, this is just a standard error, right? That's how we calculate our standard error for a sample mean. So if I take my x bar and I subtract 1.96 standard errors from that, then I shift this way. I'm going 1.96 standard errors to the left. At the same time, if I take x bar and I add 1.96 standard errors to it, then I'm going up by 1.96 standard errors. And that's how we calculate a 95% confidence interval. There's a 95% probability that the true population mean is in this interval. So the lower bound is x bar, the sample mean, minus 1.96 standard errors. The upper is x bar plus 1.96 standard errors. So now I have an interval because I'm subtracting and adding a little bit to my point estimate. That x bar again is my point estimate, right? But now we're doing an interval estimate. We're saying, well, I don't know. I don't think x bar probably is not giving me exactly the right answer. So I might want to add a little bit of error to my answer by subtracting and adding. Well, how much should I add? Well, let's pick a probability, 95%, and then add enough so that there's a 95% probability that the true mean, the thing we're trying to guess, is within that interval. So the margin of error is just this part of the interval, how much we're adding and subtracting. Because notice that that's the same. We're adding and subtracting the same amount because it's symmetric. So the margin of error is just this 1.96 times the standard error right here. So that's the mathematical version of it. We've already gone over how to calculate standard errors. But the intuitive version of it, which I like to point out, is always the same. How many standard errors I need to go out, that's 1.96 in this case, and my standard error. My standard error is just a calculation we make using the population standard deviation and the sample standard deviation. Now there's some other versions of this. For example, if I wanted a 95%, so what we've done right here, this is a 95% confidence interval for a sample mean with a known population standard deviation. What if I want a 95% CI for confidence interval for P, the population proportion? That will be P bar. I'm going to first calculate my estimate, my point estimate of the population, but then I'll subtract. It's going to be 1.96 again, because when we're dealing with proportions, we always have a normal distribution, times the square root. In this case, we don't know the population proportion, which is why we're going to use P bar in here. And that's the point of a confidence interval, because we don't know in this case. And the problems we did last time, we pretended that we knew. But now when we don't know, we have to actually use P bar in here. But that's just SE P bar, right? That's just that same formula we saw before. P bar plus 1.96. P bar 1 minus P bar over N. Okay? So it's basically exactly the same thing. The only thing that's going to change when we're doing a proportion is we have to remember we have a different standard error formula for a proportion. Now, what if we had a 99% CI for mu? Now we're doing a population mean again, but now notice what we've changed is that we want there to be a higher probability. That's going to be X bar minus, now I'm going to just write Z. What needs to be to the left? So if 99% now, before we did 95, if 99% is in the middle, and we use Z 0.025 equals a negative 1.96, well, now we need there to be 1% total on the outside, but we have an outside over here and over here, right? So we have to take that 1% and divide it by 2. So that's 0.5%. 0.5% in probability is 0.005. Because notice, if I move that decimal point over 2 places, I'll have 0.5%. Multiplied by sigma over the square root of N. X bar plus Z 0.005 sigma over the square root of N. So all that's changing now in this case is I have a different Z value. Note that Z 0.005, the absolute value of that, so it's positive, will be greater than Z 0.025. Because I have to go farther away. Think about these two pink lines. If there's a 95% in the middle where those pink lines are, what do I have to do to those pink lines to turn that 95% into a 99%? They have to go outwards farther, right? Because I want more area in the middle. Similarly, if I was doing a 90%, these are the three common numbers: 90%, 95%, and 99%. Those are the most common cases. CI for, let's do P this time, then it's going to be P bar minus Z 0.5, 5% to the left, because now we have 90% in the middle. What has to be the total on the outside if 90% is on the inside? 10%. What is left over? Or what happens to that 10% when we divide it between our two tails? We get 5%. And I did this wrong because I wrote it as 50%, right? We need 0.05, because when we move that 2 places over, we get 5%. Now, if this is a proportion, P bar, 1 minus P bar over N, comma, P bar plus Z 0.05, P bar, 1 minus P bar over N. So that's what that would look like for 90%. Now there's one last case that I want to look at real quick. There's a, let's do 95% for mu, but sigma, the population standard deviation, is unknown. So a couple things are going to change now. We're going to have x bar minus t 0.025. So now we're using a t distribution, which is going to be a little bit wider than a z distribution. The absolute value of t 0.025 is going to be greater than the absolute value of z 0.025 because this distribution up here gets wider when we're using t instead of z. Because in a t distribution, we have more uncertainty. And we reflect uncertainty by widening out this bell curve. So we have to go farther away when we have more uncertainty. You have to make that target, that confidence interval, bigger because you're less confident. And now this is going to get multiplied by s over the square root of n. Because we don't know sigma right here, but we don't know sigma. So how do we calculate? How do we estimate sigma? Using s, the sample standard deviation, x bar plus t 0.025 s over the square root of n. All right, so those are some different cases. In the next part of this video, I'm going to show you to actually make those calculations in Excel. But this is the logic of confidence intervals. Remember, this paragraph is really important right here. I want you to definitely spend some time thinking about that. And also thinking about how generally the margin of error always is how many I need to go out, how many standard errors I need to go out, times my standard error. But the reason things change, we have different cases, is because when we're doing a sample mean, we have this formula for the standard error, right? But when we're doing a proportion, we have a different standard error. So what our standard error is, this part can change based on the different situations, right? Because here it's different for a proportion. But it's always the same whether I do a proportion or x bar unless I have to estimate it right here. And then I use t also. What else can change? That's my standard error that was changing in those examples. What else can change is how many I need to go out. How many you need to go out, if it's 95%, then you need to go out 1.96 in the case that you know the population standard deviation, or if you're ever using a proportion, you can always use a z distribution. But how many you're going out needs to change if you need to go farther out because you're putting more probability in your interval, or it will go less far out if you're putting less probability in your interval. So how many you need to go out will change depending on those issues. How far you need to go out will also change if you don't know the population standard deviation, because you'll have to go out a little bit farther to account for that extra uncertainty. Okay, so I'll see you in Excel in a few minutes. All right, nice to see you guys again. So now I'm going to show you a couple confidence interval calculations in Excel, which is your go-to. This is how we would do confidence intervals in the real world. And these should be somewhat similar to some of your homework problems. So first I'm going to do a couple where we just know the information we need to generate the confidence interval. So this first one says, provide a 90% confidence interval for a sample average of 53, so that's x bar is 53, from a sample of 75, so n, the sample size is 75, and a population standard deviation of 18.6. So what did we need from that last video to make the margin of error? Well, we needed our standard error, so I'll call that SE. That's just going to equal 18.6, the population standard deviation, divided by the square root of 75, because that's just sigma over n. 18.6 over the square root of, or sorry, sigma over the square root of n. 18.6 divided by the square root of n, or of, which is 75 in this case. So that's our particular standard error. Now let's see, what's our z going to be? We're going to use a z statistic in this case because we know the population standard deviation. So that's the clue in this problem, that we're going to use z instead of t. We'll use t in a second in a different example. But for this one, we're going to see, and I'm going to write, for this case, I have a 90% confidence interval. So that means I want 90% in the middle of the bell curve. So that means there's 10% total on the outside of the bell curve. And so to the left of the lower value is going to be 10%. To the left of the upper value, sorry, there's 10% total in the tails of the bell curve. 90% in the middle, 10% on the outsides. But that means there's 5% in each tail, right? So notice if that I did z 0.95, so that's going to be the z value with a 95% of the area under the curve to its left. That's going to be to the left of the upper bar in our 90% confidence interval, if you think about it. Because we have 90% in the middle, 10% total on the outside. That means 5% in each tail. So if we find the number that has 95% to its left, that means it has 5% to its right, is another way to think about that. And so that's finding the upper z value. I like to find the upper one because it will give us a positive number. And so the Excel formula we can use for this is norm.in for inverse normal. So we put in a probability, it spit out the z-score associated with that probability. And so the probability I want to put in is 0.95, because the probability to the left of that upper value is going to be 95%. The mean, I'm going to use a standard normal. That's what a z is. So 0 is the mean of a standard normal distribution, and 1 is the standard deviation. So I have to go 1.648 about. So 1.645 is how far I have to go out. That's how many standard errors I need to go out from my 0 in the middle to maintain 90% in the center of the z distribution. But that would be one standard error at 1.65 standard errors in a z distribution out. But my standard error right here is 2.14. So I need to multiply. So to get my margin of error, I'm going to have how many standard errors I need to go out, that's that value right there, times what my particular standard error is. So that's how we get our margin of error. So let's do the actual confidence interval now. So the lower value, so let's see, call it CL for confidence lower, or I'll call it confidence interval L for the lower value. That equals X bar, which is 53, minus 3.532 ... CIU for the upper bound of the confidence interval is 53 plus my margin of error. Oops, I forgot to do equals. So equals 53 plus my margin of error right here. So that is our confidence interval. So what that says is our point estimate. So we took some sample, got a sample average of 53. But we know that's probably not exactly the population mean, which is what we're trying to estimate. But we can use that to determine that given those values, there's a 90% probability that the true sample mean is between 49.47 and 56.53. That's what that says. Now I want to show you another way. Excel actually has a formula called confidence. And notice there's two possibilities, confidence.norm and confidence.t. If you have the population standard deviation, or if you're working with a proportion, you can always use normal distributions or z. And so Excel refers to those as norm. So alpha, what is alpha going to be? Alpha actually stands for the opposite of confidence. So it's the area outside in the tail. So if we have a 90% confidence interval, alpha is going to be 0.1 for 10%. That's like the flip side of the confidence interval. The standard deviation is 18.6. And the size, that's the sample size, is 75. And look at that. I get the same number that I did when I did it by hand. So that's a nifty tool. Excel can just directly do confidence intervals because they're so common. People do them all the time. And so you should practice doing it this way. Sometimes your homework problems will ask you for those intermediary values. But you can just jump right using the confidence formula in Excel. So let's try another problem. This one is going to be for a population proportion and a different confidence level. Provide a 99% confidence interval for a sample proportion of 0.37. So that's our sample proportion. We took a sample of 500 people, that's N, and 37% said yes to our question or something like that. We asked them if they approve of Donald Trump's job performance, and 37% yes out of 500. So that might be what data looks like after you collect a sample. So we're going to need SE. We're going to need Z, and this time I'm going to do Z 0.995 because we have 99% in the middle. That means we have 1% on both sides, 1% on the outside. That means we have 0.5% in each tail. So we have 0.5% in that upper tail. Well, what's to the left of that upper tail then? 99.5%. So that's where that 0.995 comes from. Then we're going to get our MOE. I actually like doing it this way better, where I'm not calculating it. I'm kind of laying out what am I going to need. And that way it's just like kind of filling out a puzzle. We're doing the corners of the puzzle first because that's always the easiest part. And now we're going to fill in the rest. Because now it's just a matter of remembering the formulas for these different things. So standard error in this case is going to be equal to, so we have the special standard error when we do proportions, right? The square root of 0.37 times, open parentheses, 1 minus 0.37, close parentheses, divided by n, which in this case is 500, close parentheses. So that's our standard error formula for a proportion. Z 0.995, that equals norm dot INV. 0.995 is the area to the left of that upper part of the confidence interval from a standard normal distribution, so 0 and 1. And then we get 2.575. So notice it makes sense that these numbers are so much different. We don't have to go as far out when we're doing a 90% confidence interval. If we want to be accurate 90% of the time versus 99%, say you're throwing darts at a dartboard and you're designing the dartboard. You have one dartboard where you want to be accurate 90% of the time and another one where you want to be accurate 99% of the time. Which one needs a bigger target? The one that has you want more accuracy out of has to have a bigger target to gain that accuracy. So there's a trade-off in confidence intervals. If you want a higher confidence level, you have to make your confidence interval bigger. So let's see. So now we can do how many standard errors I have to go out is this number times my particular standard error is that number we calculated. So it's much smaller, but now we're dealing with a proportion. Before we were dealing with bigger numbers, right? So CI low is 0.37 minus our margin of error. CI upper is 0.37 plus our margin of error. Oops, I forgot to do equals again. I wonder why I only do it on the upper one. 0.37 plus margin of error. So now we can say, okay, our best guess is that it's 37%, 0.37. But we probably didn't land exactly on the population average, the truth. So now we can say, using that and using our sample size, we're 99% confident that the true population proportion is between 31.44% and 42.56%. That's why when you see like political polls, they're always like plus or minus 2%, plus or minus 3%. For ours, we would say plus or minus 5.56%. The way to get around that is to get a bigger sample size, by the way. Another way to make our sample or our confidence interval tighter is to get a bigger sample size. Because think about what happens to those bell curves as we get a bigger sample size from earlier videos, right? They get tighter. So we're closer to the mean without going as far away. We have higher probability around the truth when we have a bigger sample size. So we can use that confidence.norm function here too. We have to be a little careful, which I'll explain in a second. But now we have 0.01 for our alpha, the opposite of the 99%. The alpha is 1% in this case. Standard deviation, we have to type it in here, right? Because it's that formula. It's going to be square root 0.37 times 1 minus 0.37 divided by 500, and then close the square root, and then comma. We have to be a little bit careful here. No, I froze on you. Sorry, I'll just get rid of my frozen face. Make this bigger. We have to be careful here because actually we have to type 1 because it's asking for the sample size. But when we calculate our standard error for population proportions, we already included the 500 sample size. If we included it twice, we'd get the wrong thing. As we can see here, it's way too small because we already calculated it. So we know that that number with the 1 is the correct number right there. Another way to do it would be to get rid of this division by 500 and then type 500 here. So basically, whoever was writing the Excel code did not make it work for proportions the way we're using them. So you have to recognize, because Excel is just a computer, right? It's just going to do what you ask it to do. So you have to be careful when you're using the confidence formula in Excel with your sample sizes. Just for proportions is the only time that happens. All right, so those are two examples where we're given all of the parameters we need, like the sample mean, sample size, population standard deviation, or a proportion and a sample size, because that one doesn't have to give us a standard deviation, right? Because we can just calculate it. Now here's how something might look in the real world. I just downloaded Gilead stock returns. You might have heard about Gilead in the news. This is the company that has been working on one of the drugs for coronavirus. And so a lot of people have been interested in buying their stock. So I was able to download their stock data right before this from Yahoo Finance. And Yahoo Finance provides a date and an adjusted close. So that's the closing stock price today. Or no, not today, a year ago. Today is going to be down here at the bottom. The closing stock price today was $80.80. So we could, this is a sample of data. Now we could ask, what's the true average closing price for this type of stock? But investors generally don't care about prices so much as they care about returns. Now returns are the percent change in a price, and that's what you're going to actually earn if you invest in a stock. That's why they care more about that. they don't care so much about the underlying price as much as they care about how much it returns. I want the stock that returns 20% instead of the one that returns 5%, regardless of what the underlying price per share is. So the way we calculate this is we do equals. Returns are always the same way. Old minus, new, so this is the day after, minus old. That's how much the price changed from May 13th to May 14th. But we usually want that as a percentage of the earlier price. So the denominator of the fraction is how much the price changed. And then we divide by the first number to get the percent change in the price. And so that day it returned 1.4%. And now we can see there's up days, there's down days, and so forth. Down here, there might be some big days. Let's see. So they announced some results. So up here, it was up 6% on this day, 6% on that day. That's a lot for a one-day return, 8%, then 6%. That's a ton of money for one day of a stock. So this is investors thinking that they might have their hands on a cure for coronavirus, basically. And so now what we can do is say, what's the true average return for Gilead stock? And so this is the ticker right here for Gilead stock, by the way, if you want to take a look at it. But so now we have the tools to say, okay, well, we're going to calculate X bar. In this case, we're going to calculate the sample standard deviation, because this is a case where we do not know the population standard deviation, right? Because we just got a sample of data. So we don't have information about what the population standard deviation might be. Let's do a 95% confidence interval. So I'm going to do bold here, 95% confidence interval. And then I'll collect the stuff below here that I need to actually calculate that. So what do we need? We need a standard error. We need an N, so a sample size. We need a Z 0.975. So think about why I'm doing 0.975 here. And then we'll be able to get an MOE. And then we'll be able to get a CI lower bound for the confidence interval, and a CI upper. So X bar is just the average in Excel. So I do equals average, and I highlight my data, push enter. So this says our point estimate for the stock return is 0.13239% per day. That is our best guess at the average return of the stock. So you could say, yeah, invest in that in a year, for a year. And you're going to make 48% on your money. That's a pretty sweet annual return. But let's find out, because that's just a guess at the population, right? That's our point estimate of the population mean. We also need to use stdev.s for sample. This is going to give us the sample standard deviation of those values. So right there, now we have the X bar and the S, the sample standard deviation. What do we do when we need a standard error? Well, we take the sample, when we have a sample standard deviation, we take this and divide by the square root of, oh, how many observations do I have? Well, I don't know, but there's a formula for that called count. Count how many numbers I just highlighted. And just do yes, because I just didn't close the parentheses yet. And so if we want to see over here what that actually was equal to, so 251, that's how many trading days there are in a year, because people don't trade on weekends. That 251 is automatically going into the standard error formula when I use that count function. So I don't really need N because I already figured that out. So I'll just delete that, shift cells up, because we just did that over here. Maybe I should have just put that 251 right there. Now I noticed a problem I did. We can't use Z anymore. We actually have to use T. because we have a t distribution when we're using sample standard deviations. So remember, in these cases, we used z because we knew the population standard deviation. For this one, that's why we used z. Here we did a proportion, and you can always use z with proportions. Here, we had to estimate the standard deviation using a sample standard deviation. That's the case where you have to use t. Lucky for us, t dot inverse, Excel provides the same formula. We want 0.975 to the left. Now, degrees of freedom is n minus 1. So that's actually why we needed this n right here. 251 minus 1. I could just click on it and do minus 1. Or you could just type in 250. But that's just something you have to remember, is the degrees of freedom for a t distribution are n minus 1, the sample size minus 1. 1.96, that's pretty close to the 1.96 we saw before, but notice it's a little bit wider because we're dealing with a t distribution instead of a z. So we have to go a little bit farther out to account for that uncertainty. Now we're ready for our margin of error equals how many we need to go out times our standard error. CI lower equals this plus margin of error. Oops, nope, not plus, minus for the lower one, right? The upper one equals our point estimate x bar plus the margin of error. So now we see, ooh, that's kind of scary. We thought just looking at the point estimate, we were going to return like 50% a year, but equals, I should have done 251 times these numbers before, because that's how many actual trading days there are because of weekends. Now this is saying, well, the population average says your return over the year, because this is daily returns, right? So I'm multiplying up to get annual returns. This says the annual return could be anywhere between negative 37.8%, which would be really bad, or more than doubling your money, more than 100%. But a lot riskier of a stock than when you just use the average return. So that's one of the values of confidence intervals. We say, well, wait a minute. This is a random number from a random sample, so we need to be careful. And it might be better to look at a confidence interval. Okay? So I just wanted to check these and make sure I did those calculations right, because I accidentally did a plus here at first. But that's how we do a confidence interval when we have a sample. All right? So let me know if you have any questions about this. And there will be a lot of homework questions on this, and some of them are kind of tricky, but just let me know if you have questions as you get to those. I think we covered all the main cases. The one thing that they might do to you is they might give you a situation where it asks you to provide a sample size that would get you to a certain width of the confidence interval. And you got to use some algebra, or one trick to doing that is to type n right here. Oops. And just drag this down. And now we're saying, like, look, here's all these different potential sample sizes. We can make a bunch of different potential sample sizes. And then we could make our margin of error. Let's say we're doing a normal one. And let's say our alpha is 0.5, so we're doing, or 0.05, we're doing a 95% confidence interval. Standard deviation of 5, sample size, and now I just click on this and say, well, my margin of error, so I just made up that standard deviation. But if we had a sample size of 1, we'd have this big margin of error of 9. But if I click down, look what happens to the margin of error as the sample size goes up. It gets smaller and smaller. So this is a trick you can do to answer those different questions where it asks you, how big of a sample size do you need in order to do this or that? and you can kind of use varying sample sizes, then you can look for, what if we want the margin of error to be less than 0.7? We just scroll down and say, there it is. We need a sample of 196 if we want it to be less than 0.7. So that's how you might do a problem like that. But I'll save this and I'll send you this Excel sheet to play around with or take a look at whenever you have time. All right? Thanks.